Hello, this is Dr. Jack Jackson, and in this video, we're going to start a series of videos talking about t-test and t-interval. T-test and t-intervals are probably the most commonly used part of inferential statistics. You will want to think of a t-test and t-interval as just a slight modification of a z-test and z-interval, and the big difference is when the population standard deviation is unknown, which is almost always, then you're going to be using a t-test. So even though we started with a z-test, the situation that we have for a z-test is very unrealistic in most cases. The t-test is a much more realistic situation. So here are the series of videos in this section, little subsections here. This one will be the t versus z part, so we're going to compare t and z distribution. Then we'll have a video where we review some things about t distributions, which we've actually done in our previous unit. We'll then go on and talk about a one-sample t interval, show how their calculator technology works for that, which works pretty much like it does for the z intervals. Then we'll find the sample size for t interval, which is a little bit tricky. Then we'll talk about paired data, two sample intervals, one sample left-tailed test, calculator technology there. Then we'll do several examples of one sample right-tailed, one sample two-tailed, paired data t-test, two sample two-tailed test, two sample one-tailed test, and then we'll talk a little bit about the effective sample size on t-test and interval. So those are our basic topics. This section here, I would say, is, if I had to pick one thing, this is probably the most important stuff we'll do right here, talking about t-tests and t-intervals in terms of it being the most used in statistics. So you can see we're about up to problem 23 in the homework set 4 in my class, as it is as I'm recording this video. So let's go on and talk about the difference in a t-test and a z-test or z-interval and t-interval. So recall that before we can use any statistical inference procedure, we must first check that the conditions that make that procedure work are satisfied. If the conditions are met, then we can be confident, as indicated by the 1 minus alpha level, with our conclusions. However, if they are not met, then the test is not valid and any conclusion drawn from it are meaningless. Let's recall the conditions needed for computing a z-test or a z-interval. Number one, we are performing inferences about mean of a population. In a z-interval, we're constructing a confidence interval estimate of the unknown mean of the population. In a z-test, the one-sample version, we're performing a test of hypothesis comparing a sample mean to a hypothesized population mean. Number two, the distribution of sample means is at least approximately normal. This is satisfied if any one of the following hold. The distribution of individual measurements is normal or very nearly so, even for extremely small sample sizes. The distribution of individuals is unimodal, free of outliers, and not heavily skewed, and the sample size is, let's say around 15 or so. And the sample size is greater than 30 for nearly any distribution of individuals. If any one of those three conditions hold, we can assume the distribution of sample means is at least approximately normal, enough for us to use this. And finally, the population standard deviation sigma is known. So which of these conditions is typically not met? Well, performing inferences about a mean is the most commonly looked at type of hypothesis test and confidence interval. So that's very often known, not always, of course. There are other things we do, like test of proportions and variances. But testing means is probably the most common one, so that's very often met. Distribution of sample means is approximately normal. Well, that's definitely not always true, but one of these three conditions is very common. But this last one, the population standard deviation sigma is known, hey, that's very rarely set up. Okay? So So that in order for a z-test or z-interval to be used, the population standard deviation sigma must be known. And while the other conditions are realistic, reasonable, and often met, this condition is none of those things. In fact, it's highly unlikely that we will know the population standard deviation with any degree of certainty, especially if we're doing a confidence interval and we don't know the population mean. We used a z-interval and z-test to introduce the concept of confidence intervals and hypothesis tests because they are the easiest to understand and have the least amount of details. However, z-tests and z-intervals only apply to an almost non-existent real-world scenario. So how do we adjust our methods to fix the problem that the standard deviation is unknown? Well, actually, I bet you know what we do. If we don't know the population standard deviation, but we have a sample, what's the best thing to do? We just approximate the population standard deviation with the sample standard deviation, something we can find. Well, that's pretty easy. So remember that the thing that we're looking at is the z-score in a z-test and z-interval. And so that is the x bar value minus the population mean over the standard deviation of the x's, sigma sub x or sigma, divided by square root of n. And that gives us a z-score which is distributed as a normal distribution, a standard normal distribution. And so this is sometimes called the z-distribution. That's our test statistics. That's our distribution we're looking at. And everything is based on that. On the other hand, if all we're going to do is just change that sigma to an S. But what it does, it just slightly changes the distribution. And so we get a slightly similar but not exactly the same distribution. And that, of course, is called a t-distribution. We've studied this already. You will probably recall that a t-distribution is very, very close to a standard normal distribution, just with a little bit bigger standard deviation. You may also recall that a t-distribution there always has a mean of 0, but different values, different shapes, and those were determined by what we call the degrees of freedom. And the degrees of freedom in this context will always be just the sample size minus 1. So if we compute this t statistic, x bar minus mu, over s, sample standard deviation, divided by square root of n, sample size there is n, then we get this t statistic. It has a t distribution with n minus 1 degrees of freedom. So let's review. A z and t test, both cases we're performing inferences about the mean of a population. In the z or interval or t interval, we're constructing a confidence interval estimate of the unknown mean of the population. In a z-test or t-test, at least the one sample version, we're performing a test of hypothesis comparing a sample mean to a hypothesized population mean. Both the z and the t, the distribution of sample means is at least approximately normal, and this is satisfied if any one of the following hold: the distribution of individual measurements is normal or nearly so, even for small sample sizes. The distribution of individual values is a bit mound-shaped, free of outliers, and not heavily skewed, and the sample size is at least 15, and or if the sample size is greater than 30 for nearly any distribution. But the difference is condition 3. In a z-test or z-interval, the population standard deviation sigma is known. In a t-test or t-interval, the population standard deviation sigma is unknown. For large sample sizes, especially bigger than 30, there's little difference in the appropriate t-distribution and the standard normal distribution. So some people use the z-test and z-interval if the sample size is greater than 30 and just use S in place of sigma. However, the calculation is just as easy with the t-test, the answer is more accurate, and the decision of which to use is easier to make and easier to remember if we only base it on whether or not sigma is known. So in my classes, we will always use a t-test and t-interval for inferences about means if the standard deviation of the population is unknown, regardless of the sample size. It's the more appropriate one to use. In a real-world situation, you will almost never know sigma So you will almost never use a z-test or z-interval. Instead, use a t-test or a t-interval. So once again, it goes over those conditions, right? So if n is greater than 30 for any distribution of individuals, that's good. We can assume normality. For distributions that are unimodal, nearly symmetric, short-tailed, and without liars, we can still get by with greater than 15. Less than 16 if the distribution is nearly normal, mound-shaped, unimodal, nearly symmetric, short-tailed, and without outliers. And if n can be anything if the distribution of individuals is exactly normal. A t-test is considered to be robust with respect to the normality assumption, meaning it works pretty well even if the data deviates a little from a normal distribution and the sample size is a bit small. However, a very small sample from a distinctly non-normal distribution of individuals will require a different type of test, something we call non-parametric test. I don't get to non-parametric tests in my first statistics course. Problems involving inferences about means when the population standard deviation is unknown. Use the t-test for hypothesis testing and the t-interval for confidence intervals for the mean. The interpretation and execution of these problems is exactly the same as with standard normal z-tests and z-intervals with some very straightforward substitutions. T-tests and t-intervals are the most often used statistical techniques. So on the left, there's a lot of stuff here on this slide, but on the left you will see the formulas that we used for the z-test and z-interval. On the right, you'll see the modified versions that we end up using for a t-test and t-interval. And if you'll look, there's very little change. The test statistic, z star, is x bar minus mu over sigma of the x's divided by square root of n. The only thing we do over here is change sigma of x's to the sample standard deviation x. We change population standard deviation to sample standard deviation, and then that is t star, our test statistic. The distribution of test statistics over on the left, the distribution of these z-scores is a standard normal. The distribution over here on the right is a t-distribution with n minus 1 degrees of freedom. The confidence interval is still x bar minus e to x bar plus e. That's the same. We just have a very slight change in our formula for margin of error. Where we have a sigma in the formula over here, we just have an s in the formula over here. Of course, instead of an inverse norm, now it's an inverse t, this time with n minus 1 degrees of freedom. Solving this formula for n, we get inverse norm, 1 plus confidence level divided by 2, 0, 1, sigma of x's divided by e. Here, same thing. We replace inverse norm by inverse t. Here our sigma of x's is s. Everything works out. Well, not quite. Over here on the left, it actually is solved for n. Over here on the right, the problem is we have n on both sides of the equation because n is used to figure out what the degrees of freedom are here. And I have one of my videos coming up will show how we can have a technique that will sort of address that to find a size for a confidence interval, a sample size for building a confidence interval in the t-interval. It's a little bit tricky, but I'll show you that later. The hypothesis testing over here for z-hypothesis testing, if it's left-tailed, we have one critical value, which is just inverse norm of alpha, 0, 1. Left-tailed t-test has the critical value is just inverse t of alpha, n minus 1 degrees of freedom. We just changed inverse norm to inverse t, same thing. The p-value here is found from a normal CDF. We go from essentially negative infinity, which we'll use negative 10 on our calculator, up to our test statistic, z star. Standard, we have to tell it's a standard normal, so we give it a mean 0, standard deviation 1. Remember on the t, we don't give it a mean and a standard deviation. The mean is always 0. Instead of a standard deviation, we give it n minus 1, which is our degrees of freedom. So we use the t-CDF, and if you remember, I told you could always use negative 1,000 instead of negative infinity and 1,000 instead of infinity for a t distribution. It works pretty well. So we use a t-CDF, negative 1,000 to t star, n minus 1. Right-tailed, then the inverse norm is 1 minus alpha, so there's 1 minus alpha is the probability to the left, alpha is the probability to the right on a right-tailed. So same thing here, it's just an inverse t this time for the critical value. The p-value is just again a normal CDF from z star to well, infinity, but we'll use 10, 0, 1, replaced by a t CDF, t star up to 1000, n minus 1. Replace the z star test statistic with the t star, replace normal CDF with t CDF. And the two-tailed critical values, you have two of them. We have a lower one and an upper one. The lower critical value is inverse norm of 1 plus, actually that's a typo, let me fix that. Okay, now it's fixed. That's the inverse norm of 1 minus the confidence level over 2. That gives us alpha over 2 to the left. And that will be standard normal. And the upper confidence level, it is critical value is what that is. So lower critical value, upper critical value. That's an inverse norm of 1 plus confidence level divided by 2, 0, 1. That gives us alpha over 2 to the right of that. And of course, since this is centered at 0 and is symmetric, when you find the upper one and the lower one, they're opposite signs. So this upper critical value will be a positive number, and the lower critical value will be one with the same absolute value but a negative number. So do one of these, and then the other one will just have the other sign. So the p-value here is, well, if the test statistic is greater than 0, then you find the probability to the right and then double it. So this would be a normal CDF from z star to forever right, which might as well be 10, 0, 1, and then double that. Or if z star is negative, that means you're to the left of the mean, and you find the probability even further left and double it. So that would be normal CDF, negative 10 to z star, 0, 1, and then double that. And those are your p-values in those cases. Well, that translates over here very nicely. The critical value on the lower now is just an inverse t, again, 1 minus confidence level divided by 2, then minus 1 degrees of freedom. And the upper confidence level, upper critical value, these two are critical values. The upper critical value is inverse t of 1 plus confidence level over 2 with n minus 1 degrees of freedom. Once again, this one's also centered up at 0 and symmetric, so these two are just opposite signs. So figure one of these and then just do the opposite for the other one. I usually do this one here for the upper one and then just put the minus sign for the other one. Again, if the t star is bigger than 0, we just do a t CDF from t star to 1000, which is essentially forever to the right, at least in terms of practical numbers, and with n minus 1 degrees of freedom and double that. So we find the probability to the right of there, at that value or further to the right, and then double it. If the value is to the left, t star is to the left of the mean of 0, then you find the probability from there even further to the left, and then double that for your p-value. So that's 2 times t CDF of negative 1000 t star n minus 1. So this next slide here is the same formulas that we had on the right side just for the t interval and t-test. This time kind of separated into 2 columns by interval and test. And the formulas are just a little bit bigger to read, but it's exactly the same thing that I just went over. So in our next video, we're going to review our t-distribution a little bit from our last unit, and then we'll come back to actually putting it to work in t intervals.